Now we'll start the topic of what problems can happen when we classify things, what sort of data sets do we have, and we'll see everything with respect to KNN. And these concepts that we learn, they are not specific to KNN. They can be used anywhere, and most of the times it'll happen in your real world whenever you have some data set. That's why I just introduce the KNN first so that I can enter these concepts. Please focus here as much as you can, because these are concepts you will repeatedly use, I think, most of the times. Okay. Now, first thing I'll tell you is what can happen in the data set. So, types of data sets that we'll have. Types of data sets. Majorly based on number of points we'll have. This is with respect to the classification. Classification. Let's suppose we have two types of classes. We have class 1 and class 0. These are two classes. Okay, we can have two types of data sets. The first one we'll call as balanced data set. Balanced data set. And second type we'll call as imbalanced. I have also introduced these in the previous sessions. Now we'll have a detailed discussion on these things. So when we'll solve a problem in real world, what will happen there and how to solve this imbalance and stuff like that. Just to revise you what a balanced data set is, I'll just write it. Balanced data set. This terminology is applicable on this classification algorithms. It can be multi-class, it can be binary class. For the regression, even we don't care about, because there are no classes. So we have regression values there, we have continuous values there. So what is the balanced data set? So if you see, if a data set has roughly equal number of samples from each class, okay, so if a data set has a roughly equal number of points, equal number of samples, we call them, rather, samples from each class, this is called as balanced data set. Let's suppose in our binary classification problem, n1 is the number of points in class 1 and n0 is the number of points in class 0. Let's suppose n1 was 100 and n2 was 109, something like this. This is nearly balanced. Okay, so if even it was, let's suppose, 1000 and here it was some 1029, something like this, so still you see that these numbers are comparable. So if such a case happens, and that time what you have, we'll call this as a balanced set. So what are the advantages? First I'll tell you what are the advantages and why is the imbalance in data set problem. So that's why I introduced the balanced data set first. Okay, I'll write the advantage that it provides, so that you will see if there is an imbalance in the data, so what is the problem that it'll pose. The first thing is that it will give a better model performance. Why? Because it will not bias towards each class. Okay, so model performance. So mostly what will happen is, in this type of setting is the model won't get biased. Model won't get biased towards a particular class. This is like this. For example, if some people have seen a particular behavior in his environment or in her environment, so what will happen there is maybe he or she will create a bias towards that. Okay, but if somebody has seen a fair number of samples of both the things, okay, then he or she will have a holistic view of the problem, holistic view of the things. That's what happens here. So when you train a model, so if you show it equal number of points and nearly equal number of points from both the classes, let's suppose we'll take example of this spam and no spam example that we have, the running example. In our model, if you show it 1000 emails of spam and let's suppose 1020 emails of not spam, so you will still see that this our model has seen nearly equal number of examples of both the things, so that it won't get biased neither towards this nor towards this. Okay, so because it's in the sample that it considered, it actually had a balance in the classes, so we did not give it only the non-spam email, let's suppose, or spam emails only. So, and we did not make it biased. That's what I mean by model performance. I said that if you have a balanced data set, the high probability, is not guaranteed, but still high probability the model will be not, it will not be biased. Okay, and model won't get biased towards a particular class. Second thing, what, because of this, what will happen is it will reduce the risk of overfitting. Reduce the risk of overfitting. even overfitting and underfitting also. This is a simple advantage. If you see, if there is a balanced data set, the model won't get biased. Because of not getting biased, it will not overfit or it will not underfit. Okay, it will try to be a sort of good model because it has seen the enough data from all the classes. If you say, if you see it in two classes, it has seen enough data from both the classes. Now if you have an imbalanced data set, again to just define the imbalanced data set first. Imbalanced data set. So what's the meaning of this? Obviously it will be the reverse of that. So imbalanced data set refers when a classification data set has the skewed distribution. I'll say it has skewed distribution. Skewed distribution. What is the meaning of that? That means that one class has significantly fewer samples than the other class, or one class has the more samples than the other class. One class has significantly fewer samples than another class. Okay, and the class which has fewer samples, it's called as minority class. Okay, let's suppose class 1 is there, which has less sample. This is the less sample class, less sample, and then class 0 is there, which has more samples. This is more sample class. So this class we'll call as minority class. This is called as majority class. Okay, so again I'll just again reiterate this thing. So an imbalanced data set refers to the classification data set where the distribution of classes is skewed. Okay, by skew I mean that one class, let's suppose minority class, it will have fewer data samples than the other class. Okay, and let's give some real world, because this happens in real world. So what are some real world examples? Some real world examples I'd like to give. If you are detecting fraud cases, for example, let's suppose you are working in a finance for a bank and you want to classify fraud and non-fraud transactions. Obviously fraud transactions are very less, so fraud detection. So if you are detecting fraud transactions, so fraud detection, if you see, the number of frauds are very very less. And even in my experience I have seen number of frauds, if you have, let's suppose, 1 lakh transactions, among these I think 98 or more than 98% will be non-fraud. They'll be fair samples. And even in the recent case that I was doing, there were some 1.2 million records, and out of these I think around hardly around 2 to 3,000 I found by fraud. If you see the huge imbalance in the data set, so most of the samples are fair, most of the samples are non-fraud, and some samples are fraud. And now what will happen because of this is our model performance will reduce. Obviously why will it reduce? Because we are showing our model more of these examples. For most models, if you give an imbalanced data set, it's a problem for it, it creates a havoc. Why? Because our model sort of sees a lot of data from the majority class and it is biased towards majority class. But there are algorithms which are inherently good, which are good performing good on imbalanced data set. But what more in the most cases what happens is the models that we train, they're biased towards this majority class. Okay, and other real world example I can say in medical case it happens. Okay, for example, in when you were testing COVID, so that time very few percentage of population had COVID. Okay, so let's suppose out of 1,000 people I think 1% had COVID. So if you test, let's suppose, some sample of 1 lakh to 1 lakh people, so among that you will just find even 0.01% has COVID. You will see that fair non-diseased people were more and diseased people were very less. So from that you can see the real imbalance in there. So now if you train a model, so if you train a model based on this, you train a model that I'm saying I have the data, you just train it, you do not deal with the imbalance, and even you did not check it, let's suppose, for any reason. So what will happen because of this is your model will get biased towards this and you will feel our model is performing really better. Okay, even this also poses problem in the testing. So what is the first problem? I'll write problems. The problem is that model gets biased towards this. Model gets biased towards majority class. Not all models though. There are models which possess the inherent quality, they deal with the imbalance. But most of the models, they have this problem. The model gets biased towards the majority class. That's the first problem. Okay. The other problem is it cannot learn the patterns then, because it has seen very fewer samples. It does not learn patterns, or in mathematics it does not learn distribution of minority class. This is again a problem with that. And then the most important problem that I have seen in my experience, that found in the evaluation. In the evaluation there is a problem. Okay, evaluation. So when you evaluate the model, when you test the model, so I'll give you a real world example what happened, and so that you relate to it. If there is an imbalance, you have to deal with the imbalance, otherwise there is a real huge problem you will face. So what happens in the evaluation? I think you sort of understood these 2 points. So when you show a lot of data of one class, so obviously our model would get biased towards that class, and now you have very fewer samples of a minority class, and we cannot learn its distribution, we cannot learn its pattern. The model cannot basically learn by seeing only very few samples from that. Okay, what happens in the evaluation? Let me tell you an example. Let's suppose we trained a model. The model is really crap, it does not do anything. It spits out the label of majority class. It just spits out one. One means, let's suppose 1 is our majority class and 0 is our minority class. This is our majority class. This is our minority class. I trained my I did not actually, the model was such that it was not trained at all. It was untrained model, total rubbish model. But only thing it was doing is, whenever it was queried for a point, it was giving majority class. Let's take the example of fraud now. Now, if you see fraud, so let's suppose we have this data n dn. It has some 990 samples of non-fraud. From let's suppose 1 is non-fraud and 0 is fraud, and that means 10 samples were for fraud. This is the real world case, let's suppose. And now even when you test it, let's suppose you split this data. Now you split this in d-train and d-test. So in the test, if you, let's suppose we did something like this. In the test we had some 100 points, among them 99 were from the non-fraud and 1 was for fraud, and rest points in here there was a distribution like this, some data points, some here. So what it did is, our model, we did not train it at all, but what it was doing is, it was just giving the label as this majority class 111. If you just perform test evaluation on this data set, so for 99 samples it will give correct answer. Okay, and if you now just measure the accuracy, so the accuracy will be 99%, and because we just got one of these wrong. That's what the problem these imbalanced data sets create. Did you see the problem? Now you have really dumb model. The model was not doing anything, it was just giving out the majority class label. Even on the test data set that we had, we just tried to keep the same sort of distribution. Now here, for these 99 samples, it was giving 111, and it was getting the right answer for this 99, and for this it was getting it wrong. Now you saw that accuracy is not a good measure over here. Did you saw it? Accuracy is not a good measure. How many of you
Yes, sir.
agree that accuracy is not a good measure? So if somebody says that I'm believing, when most and I'll just pause the recording over here. So my point being is that you should not rely on the accuracy always, particularly in terms of this fraud detection, in terms of this medical disease detection or something like that. So you should be really clear with what the metrics that you use, and you should be able to even answer the questions based on that. If somebody asks you, why have you used this type of metric, you can say, because my data set was imbalanced and accuracy would not work. Why would accuracy not work? You can give the example. You can say that if I have a classifier which performs terrible, it just gives 1 1 for all the things, and if 99% the samples are from that class, and even if the model is not even trained, still it gives 99% accuracy. So that time this accuracy metric is not. That's why we have very difficulty in evaluating such data sets if we have a real imbalance in it. I hope that you saw where is the problem with this imbalance. Can I move ahead?
Yes, sir.
Okay, I also want to show you this imbalance visually. I think I had some code written for that, if you see it. So I will just show you an image so that you get this into a head once and for all. So when we visualize data set in 2 features, you will see something like this. Here we have 3 classes. We have class 0, class 1 and class 2. Okay, so this is what will look like if they have only 2 features, feature 1 and feature 2. Here you will see a lot of number of samples in here, and here you see a very less number of samples. And again here you see, again like similar to this green, it's still an imbalanced data set because 3 classes, this is our majority class now in this. This is a very huge number of points. If you see in these three classes, more or less the number of points are similar. Okay, so this is as balanced data set. Because before doing anything with, before training any model, what you have to do, you have to visualize your data set. If it has two features, maybe you can use some code and plot these figures and you will see this, or there is a huge number. And then you also do that data set dot shape and something, and you find how many samples I have from each class, value counts. There are a lot of functions for not a function that we have seen in NumPy pandas, and from that you can easily guess if the data set is balanced and imbalanced. I just wanted you to show this figure so that once and for all you get a picture into your brain, so that you will recognize this. If you saw something, somebody presenting something and he showed something like this, you can directly clarify that this is an imbalanced data set. Okay, am I clear with this?
Yes, sir.
Okay, nice. Now we have to deal with this imbalance, so I'll write strategies to deal with imbalance. How to deal with imbalance. This is our next topic, how to deal with imbalance. Now you saw there are a lot of problems if our data set has imbalance, and we need to deal with the imbalance. The first technique that I'll teach you guys, because we'll again and again revisit these topics, but based on the understanding that you right now have, I'll introduce the topics that you can understand, and after that we'll again come with the advanced techniques of how to deal with the imbalance. Right now the background that you have, the things that you can understand, I'll introduce only those, but believe me that I'll again revisit these topics. Why? Because they are so fundamental, and whenever you do anything in machine learning, and that time you will use these sort of things. The first technique how to deal with imbalance is called as resampling. This is the first technique that we'll learn about. So what is resampling? So resampling basically adjusts the class distribution. So it adjusts the class, or maybe adjusts the distribution of samples. I write distribution of samples for each class. Now how we are dealing with this is, we said that inherently this data set is imbalanced. Now I'll create a balance in the data set. That's why I'm saying resampling. I'll resample things, as in the fraud case or in the case of medical disease detection. So we had something 1010 from class 0, class 1, and we had a huge heavy imbalance. So what I said is, I said I'll sample the data in such a way so that I'll make it balanced. Okay, it was imbalanced, I'll make it balanced. That's why I'm resampling it. Again, you guys should be able to come up with the because you saw the problem. Now you should be coming up with a solution yourself. So I'll ask you guys how to resample it. What are the techniques? The first, I'll ask Amir, what do you suggest? What should we do? Because this is a class, let's suppose 1, this is a class 0. What can I do so that I make the data set balanced? The easy problem.
Yes, sir. So, like we did in K-fold cross validation, we will split into K-folds.
Mm-hmm. Okay, basically what we are trying to do there, we're trying to reuse again and again. You actually hit the right nail though, but you had to like articulate it better. We want to reuse the things that we already had. So what we'll do is,
Yes, sir.
we'll reuse these class 0 samples more. Okay, that technique is called as oversampling. Okay, what is that called? As called oversampling. So if we have something like this, we had this class, this was our, let's suppose, majority class. If I just show you visually, because why I like to show visually is because these things last longer with you. So whenever you will study about these, and these pictures will pop up into your head. Let's suppose this was our minority class. Okay, so what am I saying is, in oversampling we increase the number of instance of minority class. We'll increase these number of minority class. How will increase? We'll again take more samples like this. Okay, as for example, let's suppose we have 10 samples over here. We'll make it 20. Why? We'll count each sample 2 times. Okay, now we are showing the same sample again and again to the model. Okay, this is what is mean by meaning of oversampling. Just to write the definition of oversampling, it involves increasing number of samples in the minority class. In the minority class. Really nice observation by Amir, because he at least remembered k-fold cross. There also we did the same thing. We use something again and again for the validation set and the training set also. So similar thing in here. What we are doing is, in the minority class we are using these points again and again. This can be achieved by duplicating existing samples. So whatever we had, we duplicate them. Let's suppose we want now 100 samples of this. We'll take 10 each sample 10 times, because we have 10 samples over here. If we want 100 samples, so we'll take 10 samples each of these things. Okay, this is one of the techniques. And what is the other technique? That's called as undersampling. We're saying, let's suppose we have enough data. So we have enough data of this. Let's suppose 10 was a number. Let's suppose we had 10,000. Let's suppose 1,000. We said minority class we have enough data samples, but in majority class I can remove somehow these data points. Okay, so what I'll do is, in undersampling, what I'll do is I'll take roughly equal number of samples from majority class as are there in the minority class. Okay, that is what I mean by undersampling. So undersampling involves reducing the number of instances. So it involves reducing of number of samples from majority class. So what you will do is, if you have, let's suppose, more number of samples over here, you will just take these 1,000 and maybe you will take some 1,100 samples from here, and you will say you will take these samples randomly. Okay, most of the time you take them randomly. So undersampling involves reducing the number of samples from majority class so as to balance the class distribution. So usually we'll take it randomly. I'll just write it so that in the notes you'll write it. We usually take it randomly to preserve the distribution. Okay, so that is one of the things. We did oversampling, we did undersampling, and in the oversampling we again have one more technique. Okay, in oversampling I would like to, there is something called a synthetic minority oversampling technique. You might come across this. So in this oversampling there is a technique called as SMOT, SMOT. So what is the meaning of this? This means synthetic minority synthetic minority oversampling technique. So what it does is, it basically does the interpolation. So what is the meaning of interpolation? Let me tell you. So first we'll see what interpolation means. Interpolation and what is extrapolation. There are two terms, interpolation and extrapolation. And we'll see both of these terms, so that because these are used in mathematics a lot, the interpolation, in physics even. So you might have heard about these. Have you heard about these terms? At least by name?
Yes, sir. I had used this one in.
Fill that
Yes,
not
sir.
not now not a number, huh?
Yes, sir.
So do you know the meaning of interpolation? Let me teach you
No,
what interpolation
no.
is.
Oh,
That's why I told you to do the assignments, because fill those not value not number values. I on purpose gave this interpolation, interpolate these values. So let's suppose we have some values like this, and we have something like this. Okay, what interpolation means is, now you have these samples. Okay, if you want to sort of get the samples so that they respect the distribution like this, so what we'll do is we'll just connect these things. You'll say now the points can be over here also, so points can be over here. Okay, you just interpolate it. So within the graph, for example, you have this point, you have this point. Now you know that points can lie within them also. So this is sort of like a rough definition of interpolation. I don't want to get into mathematical details, otherwise it will take again a lot of time. But just understand this: if you have number of points somewhere, so what you try to do is you try to fill the space where the points were not there. Let's suppose you had some points like this. Okay, you have points like this. You still say that I can add some points over here. These also are points which belong to red class, because this is what distribution shows. Distribution shows there are red around that area, and if I just get some points like this, similarly we did something like this. I just interpolate it where there are some missing values. I'll just interpolate the values over there. This is called an interpolation. What is the meaning of extrapolation? So if you see a pattern, you extrapolate it. Okay, extrapolation means, so for example, you see a pattern like this. You see some pattern like this. Okay, you see something like this. If you see some pattern like this, so what you try to, you see like pattern is going this way, this way, this way. So in the future I think it will happen this way. So this is called as extrapolation. You are just trying to predict what will happen in the future based on what is the pattern that you have seen, the prediction that you see. So even that's why in many of the experiments you say by extrapolation we are saying this. Extrapolation basically means if we find the pattern till this point, I think this pattern will continue and we'll extrapolate this graph. Okay, that's called extrapolation. Interpolation means you just fill the values that are within, and extrapolation means you fill the values that you haven't seen. Okay, if you see the timestamps right here. So in interpolation, you will fill the values which are in the past. In extrapolation, you will fill the values which are there in the future. So is this concept of extrapolation, interpolation clear at least to some extent? Now, if you understood this, what is the meaning of interpolation roughly? What is the meaning of extrapolation? SMOTE actually does this. So what is the meaning of this? It is synthetic minority oversampling technique. Now, if you see that we're duplicating in the oversampling, what we're doing is we're duplicating the samples. But duplicating the samples that does not benefit the model much. Okay, it does not. It benefits some models, but for some models it does not benefit. So in SMOTE, what do we do is we do this interpolation. So roughly, what do we do is this again is a mathematical technique. I won't go into the mathematics, but someday once you are mathematically mature, that time we'll go over this technique again. So for example, we have some samples over here like this. Now what we'll do is we'll interpolate this sample. We'll say this sample also will belong. This is a synthetic sample now. This sample was not in the data set. We created the sample. But this sample is having high probability that this will belong to this class. But as a new sample, we actually gave it the features. Okay. And for example, we'll interpolate. Let's suppose these two things. We'll find a sample over here. Okay. We'll say we created these 4 samples within this cluster. Now these are synthetic samples. These are nowhere present in our data set. But by the method of interpolation, we create these things and we said these yellow points have high probability of being in that class because we interpolated them. That's why we can include them in the data set. That's why this is called as synthetic minority oversampling, because in the minority class we'll do the synthetic generation, but synthetic generation by the means of this interpolation will interpolate these things. Okay, that's why it's called as synthetic minority oversampling technique, as these points are not there and we are creating these points by the method of interpolation. I hope that this is clear. The first method and the first way to deal with the imbalance was to create a balance in the data set. So how did we do that? We resample the data set and we adjust the distribution of the samples for each class. The two techniques that we saw was oversampling and undersampling. In undersampling, we undersampled the undersampled. In the undersampling, we undersampled the majority class, so that if there are more samples of majority class, we'll sample roughly around the number of samples which are there in minority class. And then in oversampling, we oversampled the majority class. Or in normal oversampling, what do we do? We just duplicate the samples that we had from the minority class. And in the technique that we named as SMOTE, synthetic minority oversampling technique, so what we did in that, we just oversampled the synthetic minority oversampling that we did, because we created some synthetic samples in here. I hope this is clear. Is it clear?
Yes, sir.
Okay. There are a lot of techniques. One more technique that I'd like to introduce. This is called as class weights. So we'll assign this is called as class weights. So what is this class weights? So now in order to address this imbalance, we know that now we can resample. We can again increase, decrease data samples. One more thing that we can do is we can penalize the model. So if we have a model and if we want our model to be perfect, if it makes mistake in a minority class, we'll penalize it heavily and we'll say do not make mistakes in the minority, so that we'll make it forcefully bias it towards the minority class. And what is the meaning of this? It penalizes mistakes of minority class. Minority class is more heavily penalized. I'll write. It heavily penalizes mistakes from minority class. So for example, let's suppose we're training a model. So you now know that we have cost function in that. So what cost function does is, so it just evaluates the model and from that it adjusts their parameters. And we penalize if it makes some misclassification. So what I'm telling you is that you heavily penalize. For example, now if it makes mistakes in a majority class, you'll penalize it somehow. And if it makes mistakes in the majority class, you heavily penalize it. Let's suppose we'll have a metric like this. I'm saying if you penalize, if you got one sample from the majority class wrong, let's suppose you penalize it with, let's suppose, number 5. But if you got one sample from the minority class wrong, you uh, you actually penalize 50 times more. or something like 10 times more. This is the number of metric I'll use. This is some metric, and this is number of samples. This is from the class which it got wrong. If there's a misclassification in the majority class, let's suppose we penalized with some number 5. So I'm saying in the minority class, if you made a misclassification, then penalize it with 50. That means 10 times penalize it. Okay, this is how I assign class weights. So this addresses the imbalance. Now you sort of make the model inherently look at this. You say ki if you have an imbalanced data set, and now if you got the majority class wrong, that's okay. You have to penalize it. But when you get the minority class wrong, penalize it heavily. Okay. So what it does is I'll write it. So class weights are incorporated. Class weights are incorporated in loss function, or incorporated in loss function, which we also call as cost function, which we have seen for, I think, Canon. We also made a cost function for that, and we assign. So class weights are incorporated in loss function, and this by assigning, I'll write by assigning higher weights to the minority class. What will happen because of this? So what will happen? So the model is encouraged to focus. Actually, we encourage the model to focus more on correctly classifying these classes. So it can be seen in two ways. So this thing encourages model to correctly classify the minority class. Okay, it encourages it, or it discourages the model to incorrectly classify. If it is an incorrect classification, it will heavily penalize it. Why is it important? Why? Let me tell you why. Let's suppose we have some patients. We have some 100 patients. Among these, 90 are non-diseased and 10 people are diseased. Okay, just think about the real world scenario. Okay, why do we assign class weights? So that this gets sort of painted in your brain. So let's suppose you are dealing with and you are working for a hospital, and that time what happened, and there is a unique disease. Let's call it disease X. Some X disease was there. Now you took 100 people, which are subject people, and you are trying to see classify disease and if these people are diseased or not. But in actually, this is a ground reality. This is ground reality. 90 people actually are not diseased, and 10 people are diseased. Okay. So what you do is you predicted something. What did you predict? Tell me which prediction is good and why. Because I want you guys to arrive at the solution. Let's suppose out of these I predicted one person is diseased. Here I predicted one person is not diseased. For rest of the things I made right thing. So I made right classification. But this is, let's call this diseased, non-diseased. These are two things that I'll call them. So here I make one misprediction. I said this one person is diseased. Okay. Here I said this one person is not diseased. In the real world scenario, what would you tell? Like, is this a heavy penalty on me, or is this a heavy penalty? Consider it as some, you are detecting some disease, and this disease is fatal, because the disease, people will sort of get some heavy infection or something will happen to the body, and they'll after all die. So here I made a misclassification. Also here I made a misclassification. So which misclassification will you assign more weight, and why?
So non-disease.
So you will assign this more weight.
Yes, sir.
Why? What is the reason for that?
It may be fatal, like
Because the disease is fatal, and I
yes, sir.
don't want to get any misprediction in this class. Okay, it's
Yes,
okay
sir.
if I have to, if I'll mispredict something in this class. Why? Let's suppose this guy now underwent some treatment. Okay, because I predicted it was diseased, but actually in actuality he was not diseased at all. But still he got some treatments. If he got treatments, and maybe there will be some little adverse effects by the treatment, but still these treatments won't kill the guy. But in this case, if you see, if you mispredict the guy, so what will happen is he won't undergo the treatment, and this guy won't be given the treatment. So what will happen is eventually he'll die. That's why we bias our model towards this. We say assign more class weight to this. Okay, because we will be lenient towards this. If somebody is not diseased, we probably will say he is diseased. Why? Because then there will be chance we'll treat him, but treatment will do something to his body, but it will not be deadly. But if you see over here, if you just missed one person who had disease actually, it is huge impact on the hospital, on his life, maybe on his relatives or something like that. That's why you do not want to miss this class. That's why you'll penalize the model over this. If your model is making a single mistake, you will heavily penalize it. But if it's making mistake over here, you'll say it's okay, because if this guy gets treatment, he'll still be saved, because treatment won't have such an adverse effect. But in this case, not treating the patient will will cost his life. So it is better to penalize the model more. That's why we assign more weight to this minority class. This is just one real world example which I took the medical case, and you will see these class weights assigned differently, and you will see in the fraud detection where we have this imbalance, you sort of do this. So how many of you understood this now? Why is it necessary to encourage the model to correctly classify the minority class? Okay. So that's why we sort of penalize heavily the model, so that we encourage it to classify this minority class correctly, because otherwise it will have repercussions. If you see in the real world, it will have a heavy impact. That's why you sometimes assign these class weights. Even if you see this scikit-learn library there for different algorithms, like if you see this SVM in there, and if you see k-nearest neighbors or something like they'll have this class weights, because you want to get the model biased towards a certain class, so that you penalize it heavily to not make a drastic decision. So what's the difference between this? So what is the difference between? So I'll just say what's the difference between class weights and resampling. Because many of the things I have seen, many of the people saying they are same. That's why I'm addressing it explicitly. I've seen many huge following people who are like highly followed, and they have not made any difference on this. They have said these are something similar. That's why I want to address this. In this resampling, you actually, what you do is, the purpose is to adjust and modify the dataset so that the balance, you create a balance in dataset. So here you create a balance in dataset. This is the purpose. But here, what is the purpose? The purpose is adjust the importance. So I'll write purpose over here. So purpose over here, if you see in the class weights, we adjust the importance by giving class weights. But in resampling, we actually balance data set. We try to modify data set so that we do distribution such a way so there is a balance. Okay. What is the effect? So effect, I'll write effect. So how does it affect the model? So here, if you see in the class weights, what is the effect of this? So there's the effect is that, because it directly influences the model. This directly influences the model. Why? Because in the loss function itself, you are giving these numbers. You are giving these numbers in the loss function, because you want your model to get biased towards certain things. Okay, that's why it directly influences the learning process of the model, so that you may not misclassify the minority class. But in here, what is the effect? You modify the distribution. The sample model learns accordingly. So here, model learns accordingly. Model learns according to distribution now. Here you influence the model directly. Why? Because you are changing the cost function itself. You are assigning the weight to the class. You are assigning the weight in the loss function itself, because if model made a misclassification in minority class, you try to heavily penalize it. But in this, you do not try to heavily penalize it, but you just try to make a distribution such that it seems balanced. Okay, so this is like purpose and the effect. That's why I wanted to make it clear, this class weights and resampling, they are not the same techniques. Many of the times people will say do not resample, adjust the class weights. Okay, and even I have seen many people, even when I was like trying to code these things, and I have seen many blogs even writing this class weights, it's similar to resampling. It is not exactly, and you'll have to see your scenario. So if you are solving some real world problem like medical case fraud detection, it's better to assign class weights, because in the loss function itself, you are penalizing the model. So if you are sort of dealing with where the class weights don't matter, where you don't want to heavily penalize, but you want to get the distribution right, it's better to resample the things. Okay, have you understood resampling and class weights?
Yes, sir.
Okay, so I think, yeah, we have almost reached 8:15, so that's the time we usually close the class. So I'll just stop the recording.